So in our last lecture, we did prove the Krauss representation theorem as well as the unitary freedom of the operator sum representation. So this was quite technical, but both theorems that we proved are very important. That's why we took the time to go through the proof. And so far in this business of quantum operations, we considered very general operations. And with the Krauss representation theorem, we've proven a theorem which tells us that very general quantum operations can always be described by this operator sum representation. And in today's lecture, we now want to get a bit more precise. In particular, what we're going to look at now are some examples for quantum operations. So we now focus on qubits. So as a principal system, we now consider a qubit which undergoes some noise, and we describe this noise by quantum operations. So this is what we're going to do now. This is chapter 3.1.5, namely examples of single qubit quantum noise. So, why is this important? Well, when we, for example, discussed quantum computation, we had this circuit model where we have some qubits which undergo a unitary transformation, and then, with this unitary transformation, we do the actual quantum computation, and then in the end there's a measurement. And we always considered a perfect unitary transformation, meaning we always considered a closed system. But in reality, systems are open. And meaning that in this open system you have noise, and now with these quantum operations we have the tool to describe this noise, right? And this is what we want to do now. We want to describe noisy operations on single qubits. And once we have this description, this allows us then to detect and to correct for these errors which appear in quantum computation. Okay? This is called quantum error correction. And we're not doing quantum error correction right now, but possibly at the end of the lecture. So if there's enough time, we possibly then use all of this to do quantum error correction. But so far, we're going to restrict now to describe how noisy quantum operations can be described with this operator sum representation. So we now use the operator sum representation to describe typical noise channels of qubits. And this is relevant for the detection and correction of errors in quantum computation. Known as quantum error correction. So note that this is not the only thing where this matters. It's also important to describe in general open quantum systems, right? But for simplicity, we now restrict to qubits as the quantum systems. And since we use qubits in particular for quantum computation, this is like the first thing that came up. But in general, this is much more applicable. So in order to describe single qubit quantum noise, let me first recall how we describe a state of a qubit. So first, recall that the state of the qubit, a single qubit, can be written as follows. Namely, we have the density operator being 1/2, then we have the identity plus a real vector v times sigma, where sigma is the vector with the Pauli matrices. So, and this reads in matrix representation, we have 1 plus v set, then we have v x minus I vy, and here vx plus I vy, and 1 minus v set. So this is equation 346. So here, this vector v is a 3-dimensional real vector called the Bloch vector. The Bloch vector representation of the single qubit, so of rho on the unit sphere. Okay. So remember that the state of a single qubit can always be represented by such a vector. This vector lives within the unit sphere. If it lives on the surface of the sphere, it describes a pure state. If it lives within the sphere, it describes a mixed state. And at the origin, it describes the maximally mixed state. Okay? And well, with this, having recalled this, let me now start with our first channel, namely the so-called bit flip channel. So what is the bit flip channel? Suppose now we have a single qubit and we do something with it. For example, we send it from Alice to Bob, right? And this channel, by sending it from Alice to Bob, is noisy. And now the bit flip channel describes noise such that the bit is flipped, right? If it's 0, there's some probability that it's flipped to 1. And if it's 1, there's some probability that it's flipped to 0. And we describe it such that with probability p, there is a flip. And with probability 1 minus p, nothing happens. So the bit flip channel describes a flip of the qubit and you might remember that the flips are mediated by the Pauli X gate. So the X gate always flips the bit. So it describes a flip of the qubit mediated by the Pauli X gate. And this flip appears with probability p. While nothing happens with probability 1 minus p. So given this description, it's now easy to find the operation elements corresponding to this quantum operation. So in this case, the corresponding operation elements they are as follows. Namely, we have we call an E naught, which is square root of 1 minus p identity. And this one describes that with probability 1 minus p, nothing is happening. Because remember, in this operator sum representation, we always have some E rho E dagger, right? And then you multiply the square root of 1 minus p with the square root of 1 minus p gives 1 minus p and then the identity. So nothing happens with probability 1 minus p. So this is 1 minus p 1 0 0 1. And then we have the operation element E1, which says that with probability p we have a spin flip, okay, generated by this Pauli X gate. Let me write this out. So this is square root of p times 0 1 1 0. Okay, this is equation 3.47. Let's now see how this gate or how this channel transforms our state of the qubit. So hence the qubit transforms as follows. Then we have our quantum operation E. Let me call this E bit flip of rho is equal to E naught rho E naught plus E1 rho E1. Now let's plug this in. So E naught gives the identity. So we have here 1 minus p times rho plus, and here we have the X gate, so p times X rho X. Okay? And now what we do is we plug in rho from equation 346. So we use 346. So we get 1 minus p times 1/2 the identity plus v times sigma plus p times, and now 1/2 we have the identity gives then xx plus vx gives xxx plus vy gives xyx plus vz xzx. Okay, so let's calculate this. X squared gives identity, right? So this is the identity, meaning that this gives us x. And then we have x times y gives I times z. So this is I times z. And z times x gives I times y. So in total this gives us minus y. And here we have x times, x times z gives minus I y. And y times x gives minus I z. Gives minus, in total, minus z. Okay, so this is then equal to 1 minus p and then 1/2 identity plus v times sigma and then plus p 1/2 identity plus vx times x minus vy times y minus vz times z. Now we can put all of this together. So for the identity we have here 1/2 1 minus p and here 1 plus 1/2 p. Gives in total 1/2 times the identity. Right? Now for x we have here 1 minus p half vx, and here we have plus p half vx. Okay, so this again gives plus vxx, and now something changes, namely here we have 1 minus p half vy, and here we have minus p half vy. So this gives then plus 1 minus 2p vy times the Pauli y operator. Okay, and then similar we have 1 minus 2p yz Pauli z operator. This is equation 348. So, and what do we see now? We exactly see how this Bloch vector rescales, right? Because this again is in the same form as in 346, right? And now we see how this rescales. So the component, the x component remains the same, Vx. The y component rescales with a factor of 1 minus 2p. And the same is for the z component, it also rescales with 1 minus 2pa. So in total, by comparison with 346, this implies the rescaling, namely yx goes to yx, vy goes to 1 minus 2p vy, and vz to 1 minus 2p vz. Okay, what we see is the x component remains unaffected, but the y and z component, they decrease the larger p is, right? And it's clear that if p is 1/2, then they vanish, because what is p? P is the probability that we have a flip, right? If the probability is 1/2, then it flips, definitely, with probability 1/2. So it's the most random case. If p is 1, then it always flips, right? So then we kind of inverted our signal. So this makes sense. And now let me show you how we can represent this visually, what it does. And therefore, let me draw the Bloch sphere. So we have here x, y, and z. First, consider the usual Bloch field that we have. So this should be three-dimensional. So what we know is that what I just draw is the set of all states of qubits. So it's the set of all density operators rho which live in this Bloch sphere, in the unit sphere, right? And now let's see what our bit flip operation does to the set of all of these states, right? So we see that in x direction nothing happens, okay? So in x direction nothing happened, but there's a compression in y and z direction, okay? And what this means, that what we get out is something like this. To make this in blue, we get out this object here, okay, possibly hard to see. And this is a so-called spheroid, okay? In German it's a Rotationsellipsoid, okay? And what you see is that in x direction there's no compression, but in z and y direction there's compression. Meaning the set of all of our quantum states, if we take the set and if we act with our bit flip operation, then it shrinks, so that the set shrinks to this spheroid. So this would be the set of all E bit flip of rho. Okay, so this is how we can visualize it. So this was our first example. The second example is the so-called phase flip channel. You can already guess what it does by the name. It flips the phase. And now think about which Pauli operator does flip the phase. Then you already know what we're going to do next. So it's the Pauli set operator, right? Pauli set operator flips the phase, so meaning that if z acts on 0, we remain at 0, and if z acts on 1, we get -1. So it flips the phase of -1. And similar as the bit flip channel, the phase flip channel is generated by this Pauli set operator, meaning that in a similar way as above, we can now write down this quantum operation. So the phase flip channel flips the phase of the qubit mediated by the Pauli set operator. With probability p, while nothing happens with probability 1 minus p. Okay, it's the same setting or a similar setting as before. We have our single qubit, we send it through a channel. Suppose L is sending this qubit to Bob through a channel, and this channel has some noise, and the noise acts as a phase flip, meaning that it changes the phase of this qubit. And it acts such that it changes the phase with probability p, and with probability 1 minus p, nothing happens. So again, similar as before, we can now write down the corresponding operation elements. So this is described by so we have E naught is equal to square root of 1 minus p identity, meaning that with probability 1 minus p nothing happens. And we have E1 is equal to square root of p times z, meaning with probability p we have a phase flip. So this equation 3.50. So the outcome of the channel is as follows. I mean, we can now calculate it completely similar as before. The only thing that changes is that here we get a z instead of an x, right? So I'm not doing the full calculation again, because almost the same thing comes out. So we get that E phase flip of rho is equal to 1/2. Then we have the identity plus 1 minus 2p vxx plus 1 minus 2p vyy plus vz. So we now see that we have a rescaling of the x and y component, but not of the z component. Okay? So this implies the following rescaling. Namely that Vx goes to 1 minus 2p Vx, Vy goes to 1 minus 2p Vy, and Vz goes to Vz. Okay, and again we can illustrate this using the Bloch sphere representation. Okay, so first the set of all states. So this is rho, and then now the compression appears in x and y direction, but not in z direction. So then it looks something like this. Okay, so this is then the set E phase flip of rho. And you see the similarity, it's the very same thing, but the compression is simply in another direction. Okay, then the next channel that we consider is the so-called bit phase flip channel. Okay. And why is it called bit phase flip channel? The reason is that it is mediated now by the Pauli Y gate. So again, similar as the bit flip and the phase flip. We now consider the bit phase flip. As I said, it's mediated by the Pauli Y gate. And the reason that it's called now bit phase flip is that we can write down the Pauli Y gate as a product of the X and Z gate. And that's why it's called bit phase channel, bit phase flip, sorry. So now it's analogously the bit phase flip channel is mediated by the Pauli Y gate. So, and we can write the Y gate as I times Zx. Is it correct? I think so. And that's why it's called bit phase flip, because Y can be written as a product of Z and X, and Z was our phase flip gate and X was our bit flip gate. Okay. And this has the following operation elements. So similar as before, we have that with probability 1 minus p, nothing happens. And with probability p, we have this Y gate. So this results in the following operation. E bit phase flip of rho is equal to 1. And now we have plus 1 minus 2p vx x plus vy y plus 1 minus 2p vz z. Which yields the following rescaling. that yx goes to 1 minus 2p yx, yy goes to vy, and vz goes to 1 minus 2p vz. Okay, again we can illustrate this on the sphere. So this is, okay, it's not so nice, but I think you can see it. The set of all states rho. And now this should something look like this. So this is then the set of E bit phase flip of rho. Okay, you see that these three channels that we just discussed are very similar, and it's nice to remember how they act on this representation on the Bloch sphere, right? That they simply let this the set of all states shrink in 2 dimensions, while in 1 dimension nothing happens. We now continue with another quantum channel, which is now a bit different, but in a bit we will see the connection to our first 3 channels. And the channel that we discuss now is the so-called depolarizing channel. So what the depolarizing channel does is with some probability 1 minus p, nothing happens, right? But with probability p, what it does is it exchanges our state of the qubit with the maximally mixed state. Okay, the maximally mixed state lives in the center of the Bloch sphere, right? And so we actually, with this, we immediately see how this quantum operation looks like. So let me write this down. It's the depolarizing channel. So the depolarizing channel let me already write down what it does. It's E of rho is equal to 1 minus p times rho plus p times identity over 2. That's equation 3.55. So we see what it does is with probability 1 minus p, the state remains the same. And with probability p, we get the maximally mixed state. Okay. So the depolarizing channel replaces the qubit with the maximally mixed state. Which is the identity over 2 with probability p. While nothing happens, with probability 1 minus p. Well, the way I just wrote down this quantum operation is not in the operator sum representation, as you noticed, right? Because this second part, especially here, does not fit to our operator sum representation. So the question is now, how can we write this down in terms of the operator sum representation? In order to do this, I use an identity. So the operation elements they are obtained using the following identity, namely that identity half is equal to rho plus x rho x plus y rho y plus z rho z divided by 4. Well, and this identity holds for any qubit state rho, right? You see on the left-hand side we have the maximal mixed state. On the right-hand side there's some rho, and this equality holds for any state. If you don't believe me, you can calculate this, but we actually have done this. We almost did this calculation with the first 3 channels that we considered. Right? If you do this, because in the first 3 channels we always considered such terms x rho x, or we considered y rho y, right? If you remember this. So if you use all of this, plug this together, then you get this one. So using this, we can now get the operation elements. Such that what is this equation 355? Becomes, now let's plug this in, so we have E of rho is equal to 1 minus p times rho plus, now we have this thing here, maybe 1/4 and then rho plus x rho x plus y rho y plus z rho z. Okay, what's that? This gives us, here we have 1 minus p rho. Yes, plus 1/4 p. This gives us 1 minus 3/4 p times rho, and then plus, there's a p missing. Okay, this p must be here. Okay, here's a p missing. Plus p times, okay, now it's correct. Then plus p/4 x rho x plus p/4 y rho y plus p/4 z rho z. And now we see that it is in the form of an operator sum representation. Okay. Such that equation, this becomes that. Hence, the operation elements they are as follows. Then we have E naught is equal to square root of 1 minus 3/4 p times the identity. Then we have E1 is equal to square root of p half times x. Then we have E2 square root of p half times y, and E3 square root of p half times z. So we now got this depolarizing channel in the operator sum representation. And similar as before, we now want to see how the corresponding Bloch vectors rescale. So in order to see how these Bloch vectors rescale, we use equation 355. So it's this one here. And what we do is we plug in rho. So we plug in the expression for rho of a qubit. So this was equation 346. So using 346 in this equation 355, we get that E of rho is equal to 1 minus P, and then for rho we write 1/2 times identity plus V times sigma, and then we have plus P half times the identity. So this we can combine, that we have 1/2 times the identity plus 1 minus P V sigma. And what you see is that now the full Bloch vector rescales by this factor 1 minus P. So all components of this vector rescale. So this shows that the depolarizing channel induces a shrinking of the Bloch vector. With the following rescaling, maybe Vx goes to 1 minus P Vx, Vy 1 minus P Vy, and Vz to 1 minus P Vz. And again, the representation on the Bloch sphere is as follows. So with x, y, z. Now this was our set of all quantum states of qubits, and now this rescaling is in all 3 dimensions, so we get again a sphere, but the sphere somewhere inside here. So this is set E depolarizing channel. Now there's one interesting thing to note. So if you remember how the bit flip, the phase flip, and the bit phase flip changed the set of states, right? So what they did is they kind of squeezed this Bloch sphere in 2 directions. Now we squeeze them in all 3 directions. And what turns out is if I have a quantum channel where there is all of the three, namely bit phase and bit phase flip, well, what happens altogether, they also quench this set of state in all three directions, namely equally in all three directions. And this means that the depolarizing channel, that we get the depolarizing channel if we have a channel where there is all of the three things happening, namely bit flip, phase flip, and bit phase flip. Okay, so let me write this down as a note. So note that the depolarizing channel results from a consecutive action of the bit flip, phase flip, and bit phase flip channel. And the reason is, since, okay, suppose I take the bit flip after the phase flip, after the bit phase flip, okay, so first we act with the bit phase flip, then with the phase flip, then with the bit phase flip. You can also exchange the orders, doesn't matter. So since this one gives the rescaling, so this results in the rescaling Vx. If you do this calculation, then you will get this result here, that all of the components rescale with the factor 1 minus 2p squared. Okay, so we have 1 minus 2p squared, where p is now the probability to get a bit flip, phase flip, or bit phase flip. Okay, all of them are equal. And then in the end, if you compare now with this rescaling here p is the probability that we exchange with the maximal mixed state. So do not get confused. This is a different p than this one here, but this is the very same thing because we are rescaling all of the three components with the same factor, right? Meaning that the depolarizing channel can be described as a consecutive action of these three channels, the bit flip, phase flip, and bit phase flip channel. Okay, at this point I think we're going to do a break and meet in 10 minutes again. Let's continue with our quantum channels for noisy qubits. So before the break, we've seen a couple of channels. Let me briefly recall. So first we had the bit flip, then the phase flip, and the bit phase flip. The representation of these three were very similar. Namely, we had a shrinking on the Bloch sphere in three directions, and one direction remained unaffected. And then we had the depolarizing channel where there's an equal shrinking in all three directions, right? And the next thing that we discuss is so-called amplitude damping. And the amplitude damping describes the dissipation of energy, okay? So the picture that you can have in mind is take a two-level system, for example, an atom which is excited in the excited state, and then with some probability it can de-excite, for example, through the emission of a photon into the environment. Okay, and then this photon is gone, and we have a de-excited photon, meaning we have dissipated some energy into the environment, and we decayed to the ground state, so to the zero state. This is described by amplitude damping. So let's continue with this. So it's an important description of energy dissipation. So, as I said, an example would be this two-level atom, which can emit a photon into the environment and in this way loses this energy. And this, the process is described by the following operation elements. So this process is described by the operation elements. So we have E naught is equal to 1, 0, 0, and square root of 1 minus, let me now call this gamma. And E1 equal to 0, and then square root of gamma, 0, 0. And what's gamma? So gamma is now the probability that such a de-excitation happens. So where gamma is the probability of a de-excitation. Okay, now these operation elements possibly are not so intuitive as before. So in the phase flip channel and so on, they were quite intuitive because we said with some probability nothing happens, and with some probability there is a flip. Okay, and what you see here is a little bit of a different form. Okay, and to get a feeling of what these operation elements do, let me now consider their action on the different states. So first of all, take a look at E naught. Okay, so what it does is what we see by this entry, it leaves the state 0 unaffected. Okay. However, what it does is it changes the state 1. So it rescales the state 1 by the factor of 1 minus gamma. Okay. So let's see see this in detail. So the operator E naught, it leaves 0, 0 unaffected. But reduces the amplitude of 1. So not only of 1, also of the coherences of 1 and the coherences. So the coherences are 0, 1 and 1, 0. So short calculation shows this, namely E naught 0, 0, E naught dagger does nothing. Then we have E naught 1, E naught dagger. This now reduces the amplitude by 1 minus gamma. And E naught acting on the coherences also reduces, but now with the square root of 1 minus gamma. So this is equation 361, and this is 360. Now the operator E1, what it does is it changes the state 1 into 0. So it takes the excited state to the de-excited state. And as we see, if we do the calculation, so with E1 acting on 0, then we get 0. And E1 on 1, then we get gamma times 0. And nothing happens for the coherences. So E1, 0, 1, E1 dagger 0, and E1, 1, 0, 1 dagger is 0. 362. So what we now calculate is actually everything we need in order also to see the rescaling behavior of the Bloch vector. So together, this describes the dissipation of an excitation with the following rescaling. So we have that Vx goes to square root 1 minus gamma Vx, Vy square root 1 minus gamma Vy, and we set to gamma plus 1 minus gamma times we set. Okay, so what we see is there is a rescaling of 1 minus gamma for Vx and Vy, and in Vz direction is a bit different, so we have gamma plus 1 minus gamma Vz. So what we see is gamma is equal to 1, then Vz is equal to 1, so then we are at the ground state. And if gamma is equal to 0, well, then we remain the same. So with increasing gamma, we go more and more to the ground state 0. Okay? And this we can see by this representation on the Bloch sphere. So x, y, z. So this is the sphere, so this was the set of all states. And now after this amplitude damping, it looks something like this. So we have set of E amplitude damping. So what we see is the Bloch sphere now shrinks to the ground state, to 0, to the 0 state. Remember, 0 state is here, and here's the state 1. And there you see that this amplitude damping, in the sense that the amplitude of 1 gets damped, and we turn more and more to our state 0, which is usually associated with the ground state of a two-level system. Okay, now there's one remark that I want to do. Namely, you possibly already know this from quantum optics or from your quantum mechanics classes. So, namely, in quantum optics, this probability gamma for a de-excitation is usually given as a function of time. Okay, so let me write this down. So in quantum optics, or quantum mechanics, one often has the time-dependent de-excitation probability. Being gamma is equal to 1 minus e to the minus t over t1, so capital T1, with capital T1 called the coherence time or the relaxation time. Okay, the reason why one writes it down like this as a function of time is that the more time, so suppose you have a two-level system, suppose you have this atom, right, and it interacts with the environment. Then gamma gives the probability that there is a de-excitation. And usually if you place an atom in, you take an atom, then the probability that it interacts with your environment increases with time. That's exactly what this one tells you. If you have an increasing time, then the probability that you have a de-excitation increases, right? And the typical time such that you have this de-excitation is T1, right? And this is called your coherence time or your relaxation time. It's just for you to connect these things with those things that you possibly already learned. Okay, so now one more channel that I want to discuss is the phase damping channel. Okay. Phase damping. Now the phase damping channel is now a loss of quantum information without a loss of energy, right? So here now by this amplitude damping, we've seen that we lose our information via the dissipation of energy, right? And now phase damping is also a loss of information, but we do not lose the energy, meaning now only the phase is acted upon, but not the excitation itself. Phase damping describes the loss of quantum information without loss of energy. So an example would be now a spin state which is weakly coupled to a surrounding magnetic environment. Possibly you can, if you heard about this already, you can think, for example, of an NV center. I don't know if you heard about an NV center, which is a electron spin in a diamond structure, right? So it's simply, you can simply consider this as a spin state, and this is in a solid, so meaning in the diamond structure, and there are some other nuclei spins to which this is weakly coupled, right? And those nuclei spins, they form a environment for this electronic NV center spin. And what they do is kind of there's an interaction, and this interaction now influences the phase of this electronic spin state, right? It does not necessarily flip the state, meaning that there is no amplitude damping in the sense of a flip, but there is a damping in the sense of a phase damping. So due to this interaction, the phase of this spin is possibly affected, right? And the probability that there is such an effect on this phase is now, I now call this lambda. So, and then the operation elements are as follows. So it's E naught equal to 1, 0, 0, square root of 1 minus lambda. Okay, so if you compare with this one, the very same expression, but now we simply call this lambda. But E1 is different, namely it's 0, 0, 0, and then square root of lambda here. Where lambda is the probability for the damping process. To occur. So we can now again calculate how these operation elements act on our individual components. And of course this element E0 will act exactly in this way, right? Will be the same, but E1 will act differently, namely what we're going to see is that instead of changing the state from 1 to 0, it will decrease this amplitude, but it won't change from 1 to 0, it will stay at 1. Okay? But otherwise it's going to be the same. So similar to the amplitude damping channel. The operation elements act as follows. We have E0 acting on 0 remains 0, then E0 acting on 1 reduces the amplitude by the factor 1 minus lambda. Oh, and the coherences are also reduced. 0, 1, bigger. Lambda. And 1 acting on 0. 0 and E1 acting on 1 rescales by the factor lambda. However, we remain at 1. So hence E1 reduces the amplitude of F1, but different to amplitude damping. It doesn't change. It into 0. Okay, now there comes an interesting thing that you're also going to show in the exercises. Namely, if we now apply the unitary freedom of the operator sum representation, right? So here we have our operation elements, and you remember that there's a unitary freedom in choosing them. Well, if we do apply this unitary freedom, we see that this phase damping channel is equivalent to the phase flip channel that we just discussed. Okay? So by applying the unitary freedom of the operation elements, or of the operator sum representation, which was 3.35, one finds that phase damping is equivalent to the phase flip channel. With operation elements, now let me call them F not being 1 minus P times the identity, and F1 being square root of P times Z. And now, okay, P, where P is equal to 1/2 1 minus square root of 1 minus lambda. Okay, so if you do this, if you use this unitary freedom for these operation elements, you find then they are equivalent to those, and lambda and P are connected in this way. Okay, and if I remember correctly, this is you're gonna do this in the exercises. So hence the rescaling, we know the rescaling already. The rescaling becomes Vx goes to 1 minus square root of 1 minus lambda Vx Vy square root of 1 minus lambda Vy, and Vz is unaffected. So again, there's you possibly have heard this phase damping channel in quantum mechanics or in quantum optics, because similar as for the amplitude damping, we can now associate a time-dependent probability with this lambda, and we can again write this as 1 minus an exponential, where the typical scaling of this exponential is the so-called T2 time, or also called the spin-spin relaxation time. So let me briefly write this down. in quantum optics, in quantum mechanics. One often has the time-dependent damping probability. Lambda equal to 1 minus e to the minus t over t2, with t2 called spin-spin relaxation time. Sometimes it's also simply called T2 time. So some people, especially in experimental physics, simply call this T2 time. And the spin decoherence time that we've seen before, they often also call this T1 time. Right? So these are typical expressions. Right, with this we are finished with quantum operations. So this was the last example, and with this I'd like now to come to a new topic. And to motivate this topic, let me come back to the actual motivation that we've seen now several times. So our motivation to study quantum information theory in the very beginning was that we do have some information. Okay, say, I think we did an example with the music track. Say this is the information M. Then we encode this into a quantum state, say rho m, and then we do something with this quantum state. So we send it, sending, or storing. Okay, and then we get a different quantum state, rho prime m, okay, which we can describe via a quantum operation E of rho m. And then there's some decoding to get the information m prime. Okay? So what we just described in the last few lectures was this process here. The process of sending, storing, whatsoever, doing something with this, right? And we described this by general quantum operations. And what we get out is now possibly a different state, rho prime, so which is different to rho. And what we're going to do next is we're going to, because we want to quantify how much does this process of sending, storing, or how much does this noise which is happening in this process, how much did this affect our initial state? And to do so, we have to compare two quantum states, right? And right now we do not have those tools in order to say how different they are or how similar they are. And this is we're gonna do this next, and this is the chapter of distance measures. So we're gonna develop some measures with which we can quantify how similar or how distant quantum states are. Okay, this is chapter 3.2, distance measures. And distance measures, I mean, I can tell by my experience that distance measures are very, very important for everyone working in quantum mechanics, right? No matter if you're a theoretician or an experimentalist. For example, if you're an experimentalist and you measure some state, well, what you want to do is you want to quantify how good is this actually the state that I would ideally like to have, right? Meaning that you have to compare quantum states. So the topic of distance measures, I'm sure that if you stay in quantum, in some science which is about quantum mechanics, then you will see this every now and then. Okay, so I hope that this motivates you to study a bit distance measures, even though it's gonna be a bit dry at some point. Okay, because again we're gonna have to build up these tools, and we're also gonna prove some properties, and those proofs are theoretical, right? And possibly they're going to be a bit dry, but I hope that you stay motivated, because understanding these distance measures is very important, and you will benefit from this understanding a lot, right? So, okay, so the motivation so far is, as I told here, we want to compare quantum states. And before we now go to the task of comparing quantum states, I'd like to start with comparing classical information, right? Because we know that quantum states are a generalization of some classical information. So by classical information, this is a probability distribution. So we learned that quantum states are a generalization of probability distributions. And before we now compare quantum states, we start with, I would like to start a little bit with recalling what we know of how to compare classical information. And once we know this, we can then generalize to compare quantum information. Okay. So the topic is going to be how can we find out whether rho and rho prime are similar. And what does similar mean? Okay. So these are the questions that we're going to address. And as I already said, first we're going to do this for classical information. So this is chapter 3.2.1, namely classical distance measures. Okay, so to be honest, so far we didn't actually specify what we mean by information. Okay, so right now we do not have a clear picture what classical information actually is, okay? Because we never spoke about what information is. And we're gonna speak about this in a bit more detail, and we're also gonna quantify this information a bit later in this lecture when we speak about entropy and information. However, at this point, I'd like to introduce a little bit the picture of how we can view classical information. So what is classical information? I want you now to get a little bit of a picture of this. We're going to quantify it later on, but right now we're going to have to see what it means. Okay? And then once we understand a bit what it means, classical information, then we can compare different classical informations or probability distributions in the end. So let's stay at the question, what is classical information? And I think the most intuitive way of thinking about classical information is that classical information is how much, so classical information said it's equal to how much communication is needed in order to convey this information. Okay? So suppose there's Alice and Bob, and Alice wants to send Bob some information, and then this amount of information can be seen as how much communication is needed such that Alice can send Bob this information. Right? And okay, what is a typical scenario is that Alice and Bob do have an alphabet. Okay, they have an alphabet in common, and Alice prepares a message based on this alphabet. So this alphabet is composed of letters, and these letters appear with some probabilities, right? And now Alice prepares a message composed of these letters and sends it to Bob. And then information can be seen as how much communication is needed such that Bob can receive this message. Okay? Let me now be a little bit more precise, and let me write this down. So first, in classical theory, you can think of information being equal to how much communication is needed in order to convey it. So, and as I said before, think of Alice sending Bob a message, and suppose that they have an alphabet. Okay, an example could be the Roman alphabet. However, there's a problem because what we're going to discuss are alphabets with letters which are statistically independent. And the problem with the Roman alphabet is that in most languages, the letters are not independent, right? Think, for example, of the English language. After the letter T, it's highly probable that an H is coming, meaning that those letters are not independent in the English language. However, often it's a good approximation to say that those letters appear statistically independent. However, you can also think of different alphabets, right? An alphabet is simply a set of letters. It can be any letter you like. And a message is then built out of these letters. And what we're going to assume, because we want to stay simple, is that these letters are they appear statistically independent. And they appear with some probability. Okay, so suppose Alice and Bob share an alphabet. Say A1 to AN. So this is composed of statistically independent letters HA, which appear with probability Pj. And now it's important, and the set of probabilities P1 to Pn is known to both Bob and Alice. Okay, so those probabilities are known. And now simply assume that for an example, okay, suppose that the probability P3 is 1 and Pj is equal to 0 for all j unequal to 3, right? What's then the message that Alice prepares? Well, Alice then can only prepare the message A3, 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 and so on. Okay, because the probability of the probability P3 is 1, meaning that the message can only contain A3s. Right? And in this case, Bob is certain about the message of Alice even before he gets the message, because Bob knows those probabilities. This means that this message contains no information at all, right? Because, I mean, Bob already knows what the message will be before he gets the message, because he knows this probability. He knows that it's going to be exactly this message. Meaning this, in this case, so for these probabilities, there's no information at all in this message. Now, on the other hand, if we have Pj is equal to 1 over n for all j, well, then Bob is maximally uncertain what this message is going to be, right? Because we have equal probability for all letters. And then an example of a message would be A1, A9, A11, A4, and so on. Okay, so these letters, they appear now statistically independent, all with the same probability. Okay? And in this case, this message of Alice contains as much information as possible, because Bob is now maximally uncertain what this message is going to be. Okay? And what you're going to see here now is with this example that the information content is described by this probability distribution, namely by these probabilities with which these letters appear, right? So let's write this down. One more thing that I'd like to say. Since information is now given by this probability distribution, we can associate this probability distribution with a random variable. And this means that classical information can be associated with a random variable x, where these elements aj appear with probability pj. So this is what we learn here. So we see that information can be modeled by or via a random variable. Let's call this random variable capital X, with outcomes A1 to AN, where the outcome AJ appears with probability Pj. Hence, we are dealing with the probability distribution. In a sense, you see that classical information is nothing else but a probability distribution. And now I think it's going to be clear, because quantum information is described by a quantum state, and a quantum state is a generalization of a probability distribution, right? And classical information, as we just saw, can be modeled via a probability distribution. And now, in order to compare classical information, what we have to do is we have to compare two probability distributions. So, in order to compare classical information we have to compare two probability distribution. Say P1 to Pn and Q1 to Qn. Right. And the next time we're going to see how we're going to compare such probability distributions. And once we learned how we do this, we then go and continue with comparing quantum states, which are generalizations of probability distributions. Okay, with this I'm at the end, and I see you on Monday.